Different programming languages use different evaluation strategies to determine when to evaluate a variable declaration or the arguments passed into a function call. Today, we will be going over examples of 3 different classes of evaluation strategies, which are commonly encountered in modern language design. The simplest is strict evaluation. In strict evaluation, an expression is always evaluated completely and immediately when it's declared. Then there's non-strict evaluation, when an expression is not evaluated until it is actually used during the evaluation of the rest of the program. Lastly, we will see an example of non-deterministic evaluation, where the evaluation can occur at any time between the creation of the expression and the use of its value. The simplest evaluation strategy is constant evaluation. Const evaluation is where the expression that you are assigning to a variable or passing to a function is completely evaluated down to a single value before it is used. Because this value will never change, it is possible to replace it in all cases where it is used in the rest of the program. Here we have an example where a constant variable x is declared and set equal to 5 plus 4. In a constant declaration, the first thing that would happen is 5 plus 4 would be evaluated to 9. It would then go through the rest of the program and replace all instances of x with 9. While it isn't shown here, this replacement would abide by the normal scoping rules of this variable, so it would only replace this specific x, and if there were other variables in the program named x, it wouldn't replace those. One of the benefits of this is the compiler can optimize out parts of the program based on this constant value. So here, this if statement is unnecessary as 9 will always be greater than 0, and this fact does not need to be checked more than once. So the program can be replaced with simply print 9. However, in constant evaluation, the variable cannot be changed after it's declared. However, variable evaluation does allow for variables to change as the program executes. In this case, the variable cannot be substituted for its value in the same way that const can. Instead, an area of memory will be set aside for that variable to reside in. This area will be set by default to whatever the variable is. So in this case, where we have 2 variables x and y, it would create 2 memory locations set to the values of x and y, in this case 0 and 1. In this example, we are calling those the address 10 and the address 20 in hexadecimal. Then the rest of the program would be substituted not with the values, but with the addresses that correspond to those values. So here, the variable x would be replaced with the address 10, whereas the variable y would be replaced with the address 20. This means that whenever a change happens to the variable, it would happen to the thing stored at that memory address. This allows for changes to persist over the course of the program, as this memory address could be constantly updated. However, in this case, the early evaluation that we saw in const, where the compiler could optimize out parts of the program, is no longer allowed, as it can't be sure what will be at this memory location at any point in time. Another form of evaluation, non-static evaluation, is where a variable is not, in fact, reduced until it is used. The simplest form of this is named evaluation. As we can see here, the same example from const, where a variable x is set to be 5 plus 4, can be replaced with a named variable instead of a const variable. In this case, rather than reducing 5 plus 4 to be 9 and then substituting in 9 for x, the entire expression of 5 plus 4 would be substituted for x without being evaluated. Because of this, if x is never used, this expression needs never be evaluated. However, in this case, x would be used twice, thus 5 plus 4 would have to be evaluated twice. If we were to instead have a program where this happens rarely or not at all, as in this case where it is in an if statement which will never happen, then this variable would still be replaced, but never evaluated. Because of this, we can save the amount of time it would take to add 5 and 4. Named evaluation can be thought of as creating a function for the variable, where the function simply returns what the variable is set equal to. So in this case, a named variable x could also be thought of as defining a function to get x and have it simply return, in this case, 5 plus 4. What this would mean is that every instance where x was used can simply be replaced with a call to get x. Like other functions that are declared, getX would need to be called anew every time that it was accessed. Because of the fact that x would be accessed multiple times, most languages pass over named evaluation in favor of lazy evaluation. In lazy evaluation, rather than simply replace all instances of x with 5 plus 4, it would allocate a spot in memory where the expression that x is equal to is stored. It would then not replace any instances of x in the rest of the program. However, every time x is used, it would look at this spot in memory. The very first time x is used, this spot in memory needs to be evaluated and would be evaluated to be 9. However, subsequent calls to x would look at the spot in memory which is now equal to 9 and did not need any further evaluation to get that number. Because of this, lazy evaluation does not need to repeatedly evaluate the same expression and is much faster than named evaluation when the variable is accessed many times. It can also be used to create more complex data types like lists, which don't need to be fully evaluated before they are used. In this case, a lazy list is declared and is set to be the list of numbers that are powers of 2 between 1 and 128. This would be stored in memory. However, the list of numbers will not be complete. Because it is lazy, it will remain as only the numbers 1, 2, 4, and 128, as well as the pattern here, which is powers of 2. When we access the first element of this list, it will indeed access the number 1. However, when we access the fourth element of the list, which does not exist yet, it would need to do additional computations to find out what the element is before printing it. It would then save those computations and the results thereof, but it wouldn't need to find the numbers between 16 and 128. The list would still be partially evaluated. This can even be used to create lists of an infinite length. It would be possible to, rather than give it a list going to 128, let it go beyond forever. In this case, we could simply ask it for any index, and it would perform the evaluations necessary to get to that index. We could ask it for potentially infinitely many numbers in this way. However, there would not need to be memory for an infinite number of integers. Lastly, we will be talking about non-deterministic evaluation. Non-deterministic evaluation occurs when a variable doesn't have a value until some unspecified point in time. As the example here, we have 3 variables. Each one is the result of a network query to a website. The website may return its result at any time. And if these were all constant variables, we might have to wait an unknown period of time until x is set before getting y, and another unknown set of time before accessing z, and yet another set of time before we can proceed to the if statements. However, if these are all futures as shown here, the program will multi-thread itself implicitly, such that when x is declared, it would spin off a new thread that would attempt to access google.com. But while that thread is running, the main program would be able to continue to y, z, and the if statement without having to wait for it to finish. Thus, all 3 websites can be accessed at the same time. However, when we do reach the if statement, it requires x to have a value. At this point, the program would wait for x to get a value if it did not already have one. And the moment that x does get a value, it would print out Google is available. It would then proceed down to do the same with y and z. In practical terms, most languages have converged on using static evaluation strategies for their function calls and declarations, such as C# and Java. Purely functional languages like Haskell, as well as non-purely functional languages like R, use primarily non-static evaluation strategies, such as lazy evaluation. While the evaluation strategies that a language supports are specified by that language's specification and are unchangeably built into its grammar, it is possible to expand a language's available evaluation strategies. It is common for a language to mimic the effects of different strategies through additional libraries and third-party packages.